This is a video on the concept of adiabatic approximation. I will explain the mathematical directions or steps related to the adiabatic approximation. First of all, I'll start by considering a quantum system and a time independent Hamiltonian that governs the dynamics of the quantum system. If the initial state of the system is an eigenstate of the time independent Hamiltonian, then the state of the system remains in the same eigenstate at later instant of time, and it simply picks up a phase factor under evolution. What happens to the state of the system when the Hamiltonian is time dependent? So you have the initial state as an eigenstate of the Hamiltonian at time t is equal to 0. Will it remain as the eigenstate at later instant of time? I can ask an important question also. What will be the condition on the Hamiltonian to keep the state of the system as an eigenstate of the Hamiltonian at later time if the Hamiltonian is time dependent? We will answer this question in this video. Let's take a time dependent Hamiltonian. The state of the system governs the Schrodinger wave equation. We know that the Hamiltonian is a Hermitian operator. The instantaneous eigenstate and eigenvalue are given by equation 2. It's the eigenvalue equation. The eigenvalues are real and the eigenvectors are orthogonal and they satisfy the completeness condition. Here we have a freedom for the eigenvectors. You can choose any phase factor attached to the eigenvector. So we have that freedom in this here. To solve the equation 1, the Schrodinger wave equation, we use an ansatz given by equation 3. We know that a general state is always a linear combination of the eigenstates of the Hamiltonian. We are attaching a phase factor to it to ease our calculations. So we use this ansatz and substitute in the Schrodinger wave equation. After simplification, we get equation 4. Now we take the inner product with some eigenvector psi m of t and we get the equation 5. This gives the time derivative of the coefficient attached to the eigenvector. So to find that, we need to find one inner product psi m of t and psi n dot of t. So how to find this inner product? We will see it. To find this inner product, we'll take the eigenvalue equation, take the time derivative with respect to time. So we get the equation 7. Now again take the inner product with the eigenvector psi m of t. If m is equal to n, then we get the equation 8. When m is not equal to n, then we get the equation 9. The equation 9 gives the expression for the inner product. Now we split the equation 5 into two parts when m equal to n and n is not equal to m. So when n is not equal to m, we substitute for the inner product by the expression given by equation 9 and we have the equation 10 as the result. Now we will use the phase factor freedom for the each eigenvector and we restrain this freedom by requiring this inner product with each eigenvector is 0, the equation 11. We use the freedom of the phase vector and require this inner product to be 0. So when we have this inner product as 0, so the equation 10 reduces to the form of equation 12 where we don't have the first term, we have only the second term. So this is the expression for derivative of the coefficient of the eigenvectors. Now we apply adiabatic approximation. let's say h dot is slowly varying, then the eigenstates, the eigenvalues and the coefficients are also expected to vary slowly. Suppose at time t is equal to 0, the initial state is one of the eigenstates of the Hamiltonian at time t is equal to 0. Then as h dot is small, so for a small interval, the coefficients n of t and the en of t minus em of t is treated as constants. Then the derivative with respect to the coefficient of the n naught vector will give the equation 14. So since all the coefficients are considered as constants and the coefficient n is not equal to n naught, so all of them get to 0. So we will have derivative with respect to n naught as 0. So therefore the coefficient attached to the n naught vector turns out to be approximately equal to 1. For n not equal to n naught, we'll get the expression as 16. Now take the derivative by treating the h dot term as small and we get the expression 17. Now provided the condition that the h dot small and the expression with the derivative is compared to very small quantity, then the coefficient Cn of t attached to the eigenvectors keeps oscillating. It will not show any significant build-up. This makes the state start at an eigenstate, remains in the same eigenstate at later instant of time. This is what is known as adiabatic approximate solution to the Schrodinger wave equation. What happens if Hamiltonian is cyclic operator? What happens to the adiabatic approximate solution? So assume that there are no degeneracy, there is no level crossing. The eigenvalues turns out to be same at time t is equal to 0 or time t equal to t, and the adiabatic approximation turns out to be given in the equation 20. We know that we have used the phase freedom of the eigenvectors. Because of that freedom we have used, the eigenstate of time t is equal to 0 will not be equal to the eigenstate at time equal to t. It will get a phase factor attached to it. This phase factor is known as geometric phase.